Okay, electron configurations and the periodic table. I actually cheated a little and went ahead in the book and told you about how it works out on the periodic table. So now we're officially talking about it. Valence electrons. Valence electrons that are in the highest principal energy level or principal shell. Okay, they're the electrons that are the farthest away from the nucleus. In the quantum hotel, those are the electrons that are staying on the highest floor of the hotel, okay, that has any electrons in it. These electrons are really important because it's these electrons that are really on the outside of the atom. Those are the ones that are involved in bonding. They're involved in the interactions with other atoms, and that gives rise to the chemical properties of that particular atom. So those are really important. The valence electrons are the ones in the outer level, and then everything else in the lower levels those are called the core electrons. So if you're thinking about like an orange, the valence electrons are the rind, the peel of the orange, and the core electrons would be the juicy part on the inside. If we look at electron configurations, we need to be able to identify which are the core electrons and which are the valence electrons. So here's the electron configuration for silicon. The valence electrons are the electrons that are in this third level. So it's the 3s electrons and the 3p electrons. 3 is the highest principal shell. In the hotel, 3 is the highest floor in the hotel that has anybody staying there. And so there's 2 electrons in the s room and there's 2 electrons in the p room. So 2 plus 2, there's 4 valence electrons. All the other electrons are core electrons. So this one has 10 core electrons and 4 valence electrons. Any questions? Let's write an electron configuration for chlorine and identify the valence electrons and the core electrons. Well, how many electrons does chlorine have? 17. So let's write the electron configuration just looking at the periodic table. You start with hydrogen, and so hydrogen and helium together, that's the 1s, and it's full with 2 electrons. We go to the second row, 2s, and that one's full. And we get to 2p, and that one's also full, 2p6. Then we go to the third level, 3s2, and then we get to the 3p level. But chlorine is one short of being full there, right? If you count over on chlorine from aluminum, 1, 2, 3, 4, 5. That's how many electrons are in that level. 5. You can check the superscripts, they add up to 17. So there's the electron configuration. How many valence electrons are there? 7. These are the valence electrons. 3 is the highest shell that has electrons in it. All the electrons in the third shell are valence electrons. How many core electrons? 10. So these are the core electrons. Those are the core electrons. They're on the inside. The valence electrons are on the outside. Any questions? What group is chlorine in on the periodic table? Group 7A. Group 7A, and it's got 7 valence electrons. That's actually not a coincidence. Elements in the same column have the same number of valence electrons because their electron configurations are very similar. So we see that hydrogen, his electron configuration ends and begins with 1s1. Lithium ends with 2s1. Sodium ends with 3s1. All of the elements in group 1A have 1 valence electron. Let's look at group 7A. These are all going to end with S2P5. This one ends in S2P5. It's just this is the second level, this is the third level. All of these and the ones below have 7 valence electrons. Okay, carbon. How many valence electrons does carbon have? 4, 2s2, 2p2. Here what we're doing is we're showing you the electron configuration of the valence electrons. Silicon also. Group 4a has 4, group 5a has 5, group 6a has 6. Group 8a has 8, except for helium, because he's a little guy and he can't quite handle 8. He does have a full valence shell, though. He has 2 electrons in the 1s orbital. That's all that fits in there. So helium, like hydrogen, is often an exception to things. But the rest of the noble gases all have 8 valence electrons. It turns out that 8 is kind of a magic number for atoms. So the number of valence electrons for any main group element, except for helium, is equal to the group number, and there I'm talking about the group numbers with the letter A, 1A, 2A, 3A through 8A. Group 4A has 4 valence electrons, okay? The row number, the period, tells us what principal shell those valence electrons are in. And that's helpful, but the number of valence electrons is the really important thing. Any questions? So here's that periodic table again showing us the outer electron configurations for all the elements. And we see for the second group, they all end in S2. They all have 2 valence electrons. Now, the transition metals in here, just like with their charges that were kind of unpredictable, their electron configurations are kind of squirrely also. But these guys are nice and predictable. That transition, those transition metals, let's go back to those. So from calcium we have 4s2, and now for scandium, the next electron goes into the 3d subshell. The 3d is not considered a valence electron, even though it adds after or fills after the 4s. Because when we look at this electron configuration, 4s2, 3d10, the highest principal shell is 4. So scandium has 2 valence electrons. What we'll see for most of these is most of them have 2 valence electrons, some of them have 1. But as the d orbitals fill up, those are not considered valence electrons. Okay, so let's do a little more practice. Let's write the electron configuration for phosphorus off the periodic table. So we find phosphorus on the table, and then we're going to look at the previous noble gas. That represents the electron configuration of those inner core electrons. So this is going to be neon. And then after neon, the shells that fill, the third shell starts to fill with the S subshell. And then there's nothing here, and we come over here, and this is representing the 3p subshell. And we've got 1, 2, 3 electrons in there. So we have 3s2, 3p3. Any questions? So for those of you that like, sets of instructions, here's your instructions. How to write an electron configuration for any element looking at the periodic table. First of all, you represent the inner configuration with the symbol for the previous noble gas, and you put that in brackets. The outer electrons we determine from where the element is on the periodic table. And there's blocks. There's the S block with the 2 rows, and the D block has 10 rows, and the P block has 6 rows, not rows, columns. The highest principal quantum number is going to be equal to the row, the period that element is in. And for the D electrons, remember that you take the period -1 to get that principal level. Let's do tin. What's the element symbol for tin? Sn, right? So we got to find it on the periodic table. He's hiding down here. There he is. So, what's the previous noble gas? Krypton. So I'm going to put krypton in brackets, the symbol for krypton. And then, this one's all nice and color-coded, right? So after krypton, we're going to period 5. So this is the S block, so that's 5s2. And then we get to the D block, that's 5 minus 1, that's 4. That's full, so at 4D, full all the way across, 4D10. And then we come to the P block. We don't subtract 1 here. This is 5P, and there's 2 electrons in there. 5P2. It's like some weird code, isn't it? Unfortunately, you can't use it to send secret messages to your best friend.